Limits, a numerical and graphical approach. Let's start with a bit of review. Find the following function values given the graph of the piecewise defined function f of x shown. In part A, we want to find f of 0. So 0 is the input value. We're going to go to the x value 0, and we're going to try to find the function's value. So the function's value is located straight up at the y value 1. So f of 0 is equal to 1. Now let's find f of 1. I'm going to go to the x value 1, and I'm going to try to find the function's value. So as I go up, I'm going to skip past this y value 2 since there's a hole in the graph there, and the actual function's value is up at this y value 3. We're looking for that filled in point. So f of 1 is equal to 3. F of 2, when I go to the x value 2 and I attempt to find the function, I'm going to have a hard time because there is no function value that corresponds to the x value 2. If I go up, I recognize there's this hole in the graph. If I head down below the x-axis, there's no filled in point, just another hole. So f of 2, we would say, is undefined. For f of 5, I'm going to go to the x value 5 and try to find the function's value. So I'm going to head down, I'm going to skip past the hole in the graph and find that filled in point located at the y value, -2. So f of 5 is -2. F of 6, I'm going to go to the x value 6 and find the function. Well, it's quick to find, it's right on the x-axis. So the y value there is 0. F of 6 is equal to 0. And finally, f of 7. So I'm going to go to the x value 7. I'm going to try to find a function value or a filled in point, and I'm not going to have any luck. So there is no corresponding y value at the x value 7. So f of 7 is also undefined. Now, as we head into our discussion on limits, I want us to observe what's happening at the x value 2 and the x value 7 where we said the function was undefined. At the x value 2, I want us to notice that near the x value 2, we have two distinct pieces of the piecewise function that are not very close together. There is this jump from one piece to the other piece of the piecewise function. But at 7, where I'm also undefined, these two pieces next to the x value 7 of the piecewise defined function, they do look like they're getting closer to each other, except that they don't actually meet at a point, they meet at this hole in the graph. So even though both of these x values are undefined, different things are happening near those x values on the graph of f of x. Why do we need limits? When studying a function y equals f of x, sometimes we only know how a function is behaving near x equals c, but not necessarily at x equals c. So here's a function f of x, and right at this x value c, we don't know what's happening right at the function value. So a limit is going to ask this question, what is happening to those y values of a function as I get close to some x value? So instead of what's happening right at c, what's happening as I get close to c from both sides of c? If all the y values are getting close to the same number L as we get close to our x value c, then we say our function has a limit as x approaches c, and the limit is the y value L. So over here, from both sides of c, from the left side of c and from the right side of c, I'm getting closer to this y value L, and that is what we call a limit. So what is a limit? This is still a pretty informal definition. Suppose f of x is defined on an open interval about c, except possibly at c itself. So there could be a hole. So we have these two graphs that show us at c there could be a filled in point or there could be a hole. If the function's outputs get arbitrarily close to some y value L, for all x sufficiently close to c, we say that the function f of x approaches the limit L as x approaches c, and we write this formal notation. The limit as x approaches c of f of x is equal to L. So in both of these cases, the limit as x approaches c exists and equals L. So the bottom line is the limit still exists even if there is a hole in the graph. Let's take a look at an example. Let's consider the function f of x equals sine x divided by x near x equals 0. Notice at x equals 0, f of 0 would be equal to sine of 0 over 0, which is 0 over 0. And that cannot be determined. So the other word we have for it is we call it indeterminate. So we don't know exactly what's happening at x equals 0. So let's look at values near x equals 0 from both sides of 0 using a numerical and a graphical approach. We'll start with the numerical approach to evaluating limits. First, let's substitute x values less than 0 but getting bigger. In this case, we say x approaches 0 from the left, and we write that as x with an arrow read as approaches 0, and then a little negative symbol up in where an exponent would be. So this is read as x approaches 0 from the left. So here's a table, our numerical approach. We can see we're substituting in values on the left side of 0, less than 0. So values like -1, -0.5, -0.1, -0.001. And we're plugging those into f of x equals sine x over x. Using a calculator, we obtain the following decimals. So at -1, we end up with an output of 0.84147. Plugging in -0.5, we get 0.95885. Plugging in -0.1, we get 0.99833. And plugging in -0.001, we get 0.99999. So we can see that as we substitute in values on the left side of 0, but getting closer to 0, our y values look like they're getting closer to 1. Now we have to check the other side of 0. Now let's substitute x values greater than 0, but getting smaller. In this case, we say x approaches 0 from the right, and we write down x with an arrow and then 0 with a plus symbol up and where an exponent would be. So here's our table plugging in values on the right side of 0, numbers like 1, 0.5, 0.1, 0.001. So now we're plugging in positive values that are getting smaller, and we're taking a look at the outputs. Plugging those into sine x over x using a calculator, notice we actually get the same outputs as above when we plugged in the negative values. So we can see that the outputs are still getting closer to 1. So from these two tables, it appears that near x equals 0, the function f of x, sine x over x, gets closer to 1. Or we would say f of x approaches 1. Now let's look at a graphical approach to evaluating limits. We look at the graph of f of x equals sine x over x to determine what y value, if any, the function is approaching as we get close to x equals 0 from both the left and right side. This graph was obtained using a graphing utility. And so we can see from the left side of 0, our y values are getting closer to 1, and from the right side of 0, my y values are getting closer to 1. So the graph supports our numerical analysis from the tables above that as x approaches 0 from the left and from the right, f of x approaches 1. So from the numerical and graphical evidence, it seems reasonable to say that the limit as x approaches 0 of sine x over x is 1. So we can formally write the limit as x approaches 0 using an arrow towards 0 of our function sine x over x is equal to 1. Let's look at another example. We're going to use the graph of f of x to determine the following limits. Part A, the limit as x approaches -3 of f of x. So we're going to go to the x value -3, and we're not looking for the output value. We want to look at from each side of -3, are the outputs getting closer to the same y value? From the left side of -3, as I get closer to -3, I'm approaching the y value 4. Now on the right side of -3, as I get close to -3, I'm still approaching the y value of 4. So the limit as x approaches -3 of f of x is equal to 4. A limit only is concerned with if we're approaching the same y value from both sides. It doesn't need to have a function value right there. There could be a hole in the graph. For part B, the limit as x approaches -1 of f of x. So if I go to the x value -1 and I look at from the left side of -1, I'm getting closer to the x-axis, which is the y value 0. From the right side of -1, I'm still getting closer to the x-axis, which is a y value of 0. So the limit as x approaches -1 of f of x is equal to 0. For part C, the limit as x approaches 3 of f of x. So I'm going to go ahead and go to the x value 3. Let's look at another example. Let's use the graph of f of x to determine the following limits. For part A, the limit as x approaches -3 of f of x. We're going to go to the x value -3, and instead of looking for the output, the function's value, again, a limit asks us to think about, am I approaching the same y value from both sides of -3? So from the left side of -3, as I get close to -3, my y values are approaching 4. From the right side of -3, as I approach -3, I'm still getting closer to a y value of 4. It doesn't matter that there's a hole in the graph there, just that both sides are approaching the same y value. So the answer here is 4. For part B, the limit as x approaches -1 of f of x, I'm going to go to the x value -1, and from the left side of -1, as I approach -1, I get closer to the x-axis, which is the y value 0. From the right side of -1, as I get closer to -1, I'm still approaching the x-axis with a y value of 0. So the limit is 0, even though, again, there's a hole in the graph. Now for part C, the limit as x approaches 2 of f of x, I'm going to go to the x value 2. I'm going to go ahead and look at from the left side of 2. As I get close to 2, I'm approaching the y value -3. From the right side of 2, I'm also approaching the y value -3. So the answer to the limit is -3, and this time there was a point there, but that didn't matter. We weren't focused on reading the function's value, but rather that both sides approached the same y value as I got close to 2. And finally, part D, the limit as x approaches 4 of f of x. So I'm going to go to the x value 4, and I'm not going to fall for the trick here, which is that there is a point at 4, -1. And I'm not going to say that my answer is -1 because that's asking for the function's value. Whereas we're being asked for the limit, which is what, if any number, is the function approaching from both sides of 4. So from the left side of 4, my function's getting closer to 3. From the right side of 4, my function's getting closer to 3. So the answer to the limit is 3. But the most common mistake is to provide an answer of -1 because that's where the point is located, but that's not what a limit is asking for. Now let's look at one-sided limits. When x approaches the number c from the left-hand side, or when x is less than c, we are considering the existence of a left-hand limit, written as the limit as x approaches c, and there's a little negative symbol where up where an exponent would be of f of x. So over here on this graph, we have an example of a left-hand limit. So the limit as x approaches c from the left is equal to 1. So from the left side of c, where values are less than c, as I get close to c from that side, I end at the y value 1. Similarly, when x approaches the number c from the right-hand side, when x is greater than c, then we are considering the existence of a right-hand limit, written as the limit as x approaches c with a little plus sign up where an exponent would be of f of x. So on the same graph, we have an example of a right-hand limit. So as I approach c from the right-hand side, so I start on the right side, and then I get closer to c, I look at what is the output value I'm getting closer to, and that is 2. So that is a right-hand limit. In this example, let's consider the piecewise function f of x equals 5 minus x squared when x values are less than or equal to 2, and the function x minus 5 when x values are greater than 2. We want to find the one-sided limits at x equals 2 by the numerical table of values and verifying with the graph. So let's take a look at the numerical table of values. If we are going to look at x values on the left side of 2, that means the x values are less than 2, but getting closer to 2. So numbers like 1.9, 1.99, 1.999, 1.9999. And those are going into the function 5 minus x squared, because that was the piece that corresponded to x values less than or equal to 2. And so those outputs, when substituted into a calculator, look like 1.39, 1.0399, 1.0039, 1.0003. So we can observe here that as these x values are getting closer to 2 from the left, the y values are getting closer to 1. While in limit notation, the limit as x approaches 2 from the left of f of x is equal to 1. We have a left-hand limit. And in the second table, the x values are on the right side of 2. They are greater than 2, but getting closer to 2. So numbers like 2.1, 2.01, 2.001, 2.0001, and we're substituting those into the other piece of the function x minus 5 because that pertains to when x values are bigger than 2. And when we substitute those into x minus 5, we get negative 2.9, negative 2.99, negative 2.999, negative 2.9999. So we can hopefully see the pattern here that as we approach x values on the right side of 2 from the right, our y values are approaching negative 3. So the limit as x approaches 2 from the right of f of x is equal to negative 3. Now let's verify our answers by graphing the piecewise function. We have 5 minus x squared when x is less than or equal to 2. So this parabola is only going to be graphed when x values are less than or equal to 2. So it's only going to exist over here from negative infinity to 2. And so we can either graph using transformations, or we can go ahead and plot points, or do a combination of the two. So as a reminder, x squared is a parabola that faces up, passing through the origin with its vertex. The negative is going to reflect that parabola over the x-axis, so it'll be a downward facing parabola. And the 5 out here is going to shift that parabola up 5 units. So we're going to have this parabola with a vertex up here at 0, 5. And so now, to get the other points on the graph, we can go ahead and substitute in x values. So let's go ahead and substitute in x equals 2, since this is defined for x is less than or equal to 2. So if I substitute in 2 for x, 5 minus 2 squared, that's 5 minus 4. So I'm going to get 2, 1. as a point on the graph. If I plug in 1 into x, 5 minus 1 squared, that's 5 minus 1, I get 4. And because of the symmetry of a parabola with respect to its vertex, I can go ahead and also say that I have 2 points on the other side of the y-axis that are the mirror image of the 2 points I found. And so I can connect these together in the shape of a parabola as best I can here. So this is 5 minus x squared when x is less than or equal to 2. Now the other equation shown here is a line, x minus 5 when x is greater than 2. So this one is going to exist on the right side of the graph here. And so we can substitute 2 into the x value, but we have to be careful with what we plot. So when I plug in 2, 2 minus 5, that's negative 3. So I can go ahead and go to 2, negative 3, but I have to put a hole or an open circle there because in order to be a function, I have to have only one output for each input. And also, since this is only defined for x is greater than 2, not greater than or equal to 2, this has to be an open circle. Now from here, to find a second point on the line, I can plug in another number. I can plug in 3. 3 minus 5 is negative 2. So I have my next point, and 2 points define a line. So that's enough information. The other thing I could have done is recognize this is in the form y equals mx plus b. So the slope of the line is 1. So once I plotted this point, I could have gone up 1, right 1, up 1, right 1 to find additional points on the line. So here, does this match our numerical table? Well, as x approaches 2 from the left, my y values are getting closer to 1. As x approaches 2 from the right, my y values are getting closer to negative 3. So notice then, in summary here, that the limit from the left does not equal the limit from the right. And that's going to lead us to the next portion. We have this important theorem. The limit as x approaches c of f of x equals L exists if and only if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, and both of those limits equal L, where L is a real number. In other words, a function f of x has a limit as x approaches c if and only if the limit from the right of c equals the limit from the left of c. So from the previous example, we would say that the limit as x approaches 2 does not exist, and we would write the limit as x approaches 2 of f of x dne for short, for does not exist, because in our graph and in our numerical table we found that one side was getting closer to 1 and the other side was getting closer to negative 3. This brings us to our non-existent limit conditions. We say that the limit as x approaches c of f of x does not exist if any one of the following conditions are met. So this was just like our previous example. So a limit does not exist if the function jumps at x equals c. So we can see that there's one piece of the function and it jumps down to a totally different piece. We also say a limit doesn't exist if the function f of x oscillates too much near c, so the values of f of x do not stay close to any one number. So we have some functions that kind of go crazy. So here's an example where near 0, this function is just bouncing up and down too much and doesn't get close to any one number, so the limit does not exist. And finally, a limit does not exist if the values of f of x grow arbitrarily large to infinity or small to negative infinity as x approaches c, and do not stay close to any fixed real number. So the point is that infinity is not a number. So in other words, if the function heads off to either infinity or negative infinity when we approach x equals c from either side, then the limit does not exist. So here are some graphical examples. So at x equals c, the y values in the first example are heading towards positive infinity. They're just going up and up and up, but infinity is not a number, so we would still say the limit does not exist. And in the second two examples, we have from either side of c, the function heading towards either infinity or negative infinity. So when that happens, because those are not real numbers, we would say that the limit does not exist. And this third non-existent condition has a special name. It's called an infinite limit, and it will be discussed more in a later section. Let's look at another example. This should look familiar. It's the same crazy piecewise function we looked at in our review example to start off this lesson. But now, instead of reading function values, we're going to evaluate some limits. So for part A, B, and C, we're going to look at those three together. We're looking at the limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and the two-sided limit, the limit as x approaches 1. So we're going to come over here and we're going to focus on what's happening near x equals 1. So sometimes with these piecewise functions, there's so much going on, it can be easy to get distracted. So we really just want to focus in around x equals 1. From the left side of 1, so I'm going to start on the left, and I'm going to get closer to 1. So notice I am moving to the right, and that tends to confuse people, but just focus on the idea of starting on the left. So from the left, I'm getting closer to 2. That's the y value. So I have 1 from the left is positive 2. Now, on the right side of 1, we want to stay close to 1, but on the right side, I'm going to find the function, and I'm going to approach 1. My y values are getting closer to 3. So, since the limit from the left is 2 and from the right is 3, those are not the same value. The limit as x approaches 1, the two-sided limit, we would say does not exist. So they're not meeting at the same y value. Now let's look at parts D, E, and F together. The limit as x approaches 2 from the left, 2 from the right, and 2. So we'll go ahead and focus now on what's happening around the x value 2. We're going to start on the left side of 2. We're going to find the function. We're going to approach 2 and recognize it's getting closer to the y value 3. So we're going to go ahead and say that the limit as x approaches 2 from the left is 3. Now we're going to go to the right side of 2, find the function, and approach 2, and recognize I'm getting closer to negative 1. These are two different outputs from the left and from the right, so the two-sided limit also does not exist. Now let's look at parts F, G, and H. We're going to look at 4 from the left, 4 from the right, and 4. So let's go ahead and focus on that x value 4. And we're going to go to the left side of 4, and we're going to get closer to 4 and recognize we're getting closer to that y value 2. Now we're going to go to the right side of 4, find the function, and get close to 4. We're getting closer to the x-axis where the y value is 0. And once again, these are not the same output, so the two-sided limit does not exist. And now we'll look at I, J, and K, but separately. So these are all just two-sided limits. The limit as x approaches 5 of f of x. So if we're looking at the x value 5, we're looking at what y value, if any, are both sides getting closer to. Well, from the left side, I'm getting closer to negative 1. From the right side, I'm getting closer to negative 1. So the answer to the limit is negative 1. Even though the function's value is down here at negative 2, we don't care about that. Limits care about what we're getting closer to from both sides. Now as x approaches 6, let's go to the x value 6. From both sides of 6, I'm getting closer to that x-axis where the y value is 0. So there is a point there, but that didn't really matter. It's just about from both sides, I'm getting closer to the x-axis where the y value is 0. And at 7, from the left side of 7, I'm getting closer to 3. And from the right side of 7, I'm getting closer to 3. So even though there's a hole there, doesn't matter. From both sides, I'm getting closer to that y value 3. In this example, we want to sketch the graph of a function that satisfies the following limits. So it's kind of backwards from what we've been doing. We've been given a graph and asked to find limits from the graph. Now we're given some limits and we get to construct the graph of that function. So let's start by trying to satisfy this first limit. The limit as x approaches -2 from the left of f of x is equal to 3. So from the left side of -2, so here's -2, as I come at -2 from the left, I've got to get closer to this y value 3. Now when I sketch the graph, there's a lot of different possibilities. So all of our graphs can look very different. I can choose to approach -2 with an increasing function and get closer to 3. I can choose a constant function. I can choose a decreasing function, as long as from the left side I get closer to that y value of 3. So I'm going to go ahead and choose an increasing function. So I'm going to go ahead and head towards -2 from the left with an increasing function. And I'm going to end at the y value 3. And I'm going to choose to put an open circle there. I would suggest that anytime you're trying to satisfy a limit, that you end at an open circle, just because later on one of these conditions might tell you where to put the point. So unless otherwise stated, I would suggest ending at an open circle. All right, so the first part is satisfied. Now let's try the second limit. The limit as x approaches -2 from the right of f of x is equal to 5. So what I want to do is I want to go to the right side of -2, and I want to head towards -2, and my y values are going to head towards 5. Now I want to be careful. Notice I went just to the right of -2 and then started heading towards -2 along the x values and get closer to 5 for y values. I don't want to kind of go crazy and start way over here because I have all these other conditions to satisfy. Notice there's stuff going on around 0 and 4, so I don't want to affect what's happening over here on the graph. I want to stay close to -2. So I'm going to stay pretty close to -2, and I'm going to create a function that gets close to 5 from the right side of 2. So I'm going to make it look something like this. So again, I'm choosing to end my limit at an open circle. So from the right side of -2, I'm getting closer to 5. Now this third condition is a point. It's not a limit, it's a function value. So it says f of -2 is equal to 0. So this is telling me to go to the x value -2 and to put a filled in point at the y value 0. So it's a good thing we didn't put a point at the end of either of these two pieces, because we would have had to erase it. We need this to be the graph of a function, and that means each x value can only go to one y value. So these had to be open if this is where the point is going to be down here on the x-axis. So this function value is satisfied. Now, the limit as x approaches 0 of f of x has to equal -4. This is a two-sided limit. So from the left and the right side of 0, I got to head way down here to -4. So we want to make sure that we pick up where we left off. We don't want to have all these random line segments all over the place. So what we want to do is pick up where we left off, and we want to take that and head all the way down to -4. So I'm going to pick this up and head all the way down to -4. And that's the left side of 0 getting closer to -4, but the right side also has to get close to -4. So I'm going to stay kind of close and make sure that my right side goes down to -4. And I can choose to end at a filled in point or an open circle. We can see that this remaining piece doesn't deal with the x value 0, so we can leave it just kind of this filled in point, or you can make it an open circle. It doesn't matter. Again, our graphs are going to look maybe kind of different. So now this fourth limit is satisfied, or fourth piece is satisfied because this one wasn't a limit. And so now this fifth piece here is also a two-sided limit. The limit as x approaches 4 of f of x equals f of 4. This one tends to throw people off a little bit. So what it means is that the two-sided limit, as I get close to 4 from both sides, has to equal the function value. So this actually tells me that the limit has to meet at a point. It can't meet at a hole, but it doesn't matter where. So it's not telling me that it has to be a specific y value, just that the two-sided limit has to equal the point. There cannot be a hole. So I'm going to go ahead and pick up where I left off over here, head towards 4, the x value 4, and I'm going to, from the left side, I'm going to get closer to 2. Again, it doesn't matter what y value, I'm going to get closer to 2. And then from the right side of 4, I also have to get closer to 2. But the thing is that normally I have a choice. I can put an open circle, I can put a filled in point, but this time I don't have a choice. It has to be a filled in point. So I can leave it like this, or I can accentuate the point like this, but it cannot be a hole. So what this last condition means is that the limit has to equal the point. They have to meet at a filled in circle. Whereas here, this one told me that from the left and right side of 0, I had to go down towards -4 from both sides, but it could have been a point, or like a point like this, or it could have been a hole in the graph like this. So either one of those options was fine for this limit, but for this one, the y value it could meet at could be anywhere, but it has to meet at that point. So this is one possibility, a lot of different possibilities for how this graph can be created to satisfy these conditions. Limit laws. These are basically some rules that limits follow. So as long as the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist, then the following laws or sort of rules are true. So the limit as x approaches a of f of x plus or minus g of x, well, that's equivalent to doing each limit separately and then adding them together. The second law says that if I have the limit as x approaches a of a constant times f of x, then I can go ahead and pull that constant outside of the limit. So if it's multiplying by a constant, I can pull the constant out. 3 and 4 I'm going to lump together. These laws say that if I have the limit as x approaches a of f of x times g of x, or f of x divided by g of x, then I can do each limit separately. So the limit as x approaches a of f of x times the limit as x approaches a of g of x, and I can turn the limit of a quotient into the quotient of two limits, as long as the bottom limit is not 0, right? I still can't divide by 0. And last but not least, the limit as x approaches a of f of x to p a power. Well, I can take the limit and drag it into the power, as long as that quantity exists. So these laws or sort of rules are a way for us to compute limits rather than graphical or numerical methods. Here's an example using limit laws. Let's let the limit as x approaches 2 of f of x equal 8, and the limit as x approaches 2 of g of x equal 2. Find the limit as x approaches 2, 3, times the square root of f of x times g of x using limit laws. So here's what we're first going to do, is we're going to take this constant that's being multiplied, we're going to pull it outside the limit, and that's because of the constant limit law. The next thing we're going to do is take this limit and drag it underneath the radical, because I can take a limit into a power, and the square root is the power of 1/2. Next, I'm going to use the limit law involving products. The limit as x approaches 2 of f of x times g of x can be written as two separate limits multiplied together. Now we have used many of our limit laws, and we've arrived at a place where we can use the given information. The limit as x approaches 2 of f of x, well, that entire thing is equal to just 8. And the limit as x approaches 2 of g of x, that entire thing is equal to 2. So what we're left with is 3 times the square root of 8 times 2, or 3 times the square root of 16, or 3 times 4, which is equal to 12. Let's look at a few more examples. We have the limit as x approaches 2 of 4 is equal to, well, in order to understand the answer to this question, I've drawn a graph of the line y equals 4, which is just a constant. So notice it doesn't really matter that we're approaching the x value 2, because from both sides of any number, the y value is just 4. So in this case, from the left side of 2 and the right side of 2, I'm getting closer to 4. But we could have had the limit as x approaches 1,000 of 4, and I would still be getting closer to 4. Now over here, the limit as x approaches 3 of x, well, it turns out that that's just 3. And we can see why that occurs if we look at the graph of y equals x. Y equals x is the line that passes through the origin with slope 1. It's also called the identity function because whatever you plug in, you get out. You plug in 2, you get out 2. You plug in 3, you get out 3. So as I'm approaching 3 from both sides of 3, I'm going to get closer to the y value 3. And these two examples bring us to this theorem. For any constants k and c, the limit as x approaches c of k is just k. So the limit of a constant is the constant. And the limit as x approaches c of x, well, that's just c. I can plug c into the x. In this example, we want to compute the limit as x approaches -1 of the quantity 2x squared minus 3 using limit laws. So here, I'm going to do this all in one step. I'm going to use all the limit laws all in one step. So I'm going to write this as 2 times the limit as x approaches -1 of x all squared minus the limit as x approaches -1 of 3. So I use the constant limit law. I pulled the 2 out. I use the one involving powers or exponents. So the limit as x approaches -1 of x, all of that is squared. And then the difference limit law, so I can handle this 3 separately. So now each of the limits that's left over falls into the category of the previous theorem. So here, the limit as x approaches -1 of x, we can simply substitute in -1 into the x. So that would leave me with -1 squared, and then that 2 coefficient is left in the front. And then here, the limit of a constant is just the constant. It doesn't matter that we're approaching -1, so this is just going to be a 3. So I have 2 times 1 minus 3, or 2 minus 3, is -1. So we technically use limit laws and then use that theorem to evaluate these two limits. But what I want you to notice is that for this last example here, we could have just used direct substitution to arrive at the same answer. In other words, at the beginning, I could have taken this -1 and substituted into this x. And that would have left me at this step right here, 2 times -1 squared minus 3. And that brings us to our next theorem. This theorem tells us that if p of x and q of x are polynomials, then the limit as x approaches a of p of x is equal to p of a. And the limit as x approaches a of p of x over q of x is just p of a over q of a, as long as the denominator is not 0. So in other words, what this says is that we can just use direct substitution on limits for all polynomial and rational functions with non-zero denominators. In fact, we can actually use direct substitution on any continuous function, provided we are in its domain. But we'll talk more about that later. So for now, we can substitute in our a value into polynomials and rational functions instead of using limit laws. So in this example, find the limit as x approaches 2 of the quotient x squared minus x plus 1 all over 3x minus 2, so a rational function, without using limit laws. So what we are allowed to do in this case is just take 2 and substitute it into each x. So we have 2 squared minus 2 plus 1 all over 3 times 2 minus 2. And observe that once we apply direct substitution, we no longer write the limit notation. And so now we can just simplify. So we have 4 minus 2 plus 1 over 6 minus 2. 4 minus 2 is 2, 2 plus 1 is 3, 6 minus 2 is 4. So we end up with 3/4.